In the biomechanics of cortical bone, the yield point in a stress-strain curve A is followed by plastic deformation. B is followed by return of its original length on removal of the load. C is the point after which some permanent deformation occurs. D refers to the modulus of elasticity. E is the point of ultimate failure. And the answer is C is the point after which some permanent deformation occurs. Now let's revise a bit about this stress-strain curve. As an introduction, age-related fracture leads to a loss of mobility, an increase in mortality, and a lower quality of life. A significant portion of physiological loading is carried by the cortical shell. Thus, its role in fracture resistance and strength of whole bone is important. The whole bone strength depends on the tissue mineralization measured by clinical densitometry, but also on the micromechanical properties of bone tissue. Stress-strain curve in cortical bone. The mechanical behavior of cortical bone can be characterized by 1. An initial elastic domain where the material deforms in a reversible pattern. 2. A post-yield domain where irreversible strains and damage are produced. 3. A fracture zone where a macro crack is formed. In tension, the formation of a macro crack is a rapid event once the ultimate point is passed. The zones represent an area that is equal to the mechanical work necessary to break the bone. Zone 1 represents the elastic mechanical work, and the sum of zone 2 and 3 yield the plastic mechanical work. This figure shows the stress-strain curve. For tension, red color, compression, blue color, and shear, green color, in loading in axial direction. Mechanical behavior illustrated are elastic domain 1, post-yield or damaging is zone 2, and a fracture in zone 3 where a macro crack forms. Hardening, be it linear or exponential, describes an increase in stress after passing the yield point. Softening, in turn, is a decrease in stress usually observed after passing an ultimate value that may coincide with the yield point. Ideally, plasticity denotes an asymptomatic behavior after reaching the yield. Brittle, quasi-brittle, and ductile are descriptions whether the area underneath the stress-strain curve, that is, the energy after passing the yield zone, that is, region 2 plus region 3, is small or large respectively. Ductility refers to a material's ability to dissipate a lot of mechanical work and is the opposite of brittleness. This figure shows loading in transverse direction. The blue line depicts the ductile curve and each of the yield zone for ductile, brittle and quasi-brittle. Okay everyone, thank you and happy learning.